Namaste. Good morning. All right, guys. All right, we're coming towards the end. All right, this morning, I want to talk about the concept of a force, okay? And that's the next section in your book. It's section 12.1, which you guys should be working on today, all right? Now, when you read the book is going to define what a force is as a push or a pull. I'm going to high school it up for you a little bit, all right? Because what a force, that's what we tell the little kids in the elementary school and the middle school. What's a force? Well, a force is a push or a pull. And that's kind of vague, all right? Not that I have a much clearer explanation, but I have a little more scientific explanation, all right? And what I want you guys to know is that a force is something that causes objects to accelerate. Write that down. Forces cause accelerations. All right, so what a force is it's something that causes an acceleration. Okay, and what does that mean? Well, a force is something that will cause you to either speed up, slow down, or turn. Because remember, we did a whole lesson on acceleration, that there are three ways to accelerate, okay? Things don't, and what we're saying here is this, and it's actually pretty common sense, okay, in nature. Things don't spontaneously speed up, slow down, or turn, okay? They have to be forced to do so. All right. So if something is moving, it's going to keep on moving unless it's forced to do so. Now, this might sound counterintuitive, and this was thought that this was the way it was for a long time. Aristotle said that things come to a state of rest naturally, and that makes sense if you don't test it out. On Earth, if you throw a ball, what does it do? It eventually slows down, hits the ground, slows down, and stops. If you push something, what does it do? It slows down and stops. And then along comes Galileo and Newton, and they said, no, 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 that's not really the case. Okay, they're slowing down and stopping because there's a force involved, and that force is called friction. Aristotle didn't go there. He didn't take it that next step. Okay, so anyway, to get into this is one of the reasons why we had to teach you about vectors also. Let me get that a little bit better. All right, there's this concept of a net force. Whoops. Okay, and your book talks about this, and it's a simple concept, and it makes a lot of sense. So let's say I have an object over here, right, and some mass, and I'm pulling on it with 10 pounds of force, okay, in that direction. But someone else is pulling on it in this direction with 4 pounds of force, okay? This is physically the same exact situation as if I had one 6-pound force pulling on it in that direction. See, with the 10 going that way and the 4 going that way, because forces are vectors, vectors can cancel each other out. This 4 cancels out some of the 10, all right, not completely, but some of it, and knocks it down to 6. So this situation where you have a 10 this way and a 4 this way, in this situation where you have only a 6 going this way, are physically the exact same thing. There's no physical difference between the two situations, okay? And we call this the net force, right? We call this the net force. So you have a 10 and a 4 going that way. You have a net force of 6 going to the right, and that's how we say that, okay? And if you switch the numbers around, okay, to do another example, let's say I have a 2-pound force pulling in that direction, and then a 5-pound force pulling in that direction. This is physically the same as, see, the 2 would cancel out some of the 5, as if you had one 3-pound force going in that direction to the left, okay? So that's the concept of a net force. Now, forces can cancel each other out. So what if I had, okay, a 5-pound force going in that direction and a 5-pound force going in that direction? Well, they would cancel each other out completely. okay? And this would be the same exact situation as having an object with no force on it whatsoever, okay? When this happens, when they cancel each other out completely, we say that the forces are balanced, okay? So balanced forces are when forces cancel each other out completely, and it's the same thing as having no force on you at all. And a good example is if you just think of your own body right now, you're sitting in your chair, and you don't feel like you're having a force on, like you have a force on you. Obviously you do. You have the force of gravity on you right now, okay, and it's pulling you down. But why aren't you falling down, right? Well, because, and I want you to think of it this way, the chair that you're sitting on is pushing up, and that can happen. Inanimate objects can create what's called a reaction force. Sometimes it's called a normal force, okay? So what you have on you right now is your weight pulling down, but you have the chair and the floor pushing up on you, and the two forces are equal and opposite, and they cancel each other out. If the floor or the chair was not strong enough to cancel out the force of gravity on you, you would fall, okay? You would break the chair, go through the floor, or whatever, okay? So, but they're not, so they're balanced, okay? All right, and when you have balanced forces on an object, you have no acceleration. Balanced forces, when the forces on an object are balanced, you have no acceleration. Okay, that doesn't mean that you're not moving. You could be moving. So for example, when you're in your car, I'm going to draw the world's crappiest car, basically a box on wheels, and you have the force of the engine that is pushing the car forward, okay, transmitted through the wheels, through something called a transmission, all right? But what else is going on there? Well, you have friction holding you back. Force of friction through the air, and the air at high speeds, fluid friction is very strong. Okay, and if you don't believe me, then get on the highway, all right, in your car, and go to like a typical Rhode Island speed of 89 miles an hour, and then roll down the window and stick your face out there, and you'll find out that air friction can be very, very strong at high speeds. So that's what's going on. So if your car, if you're at a constant, let's say 60 miles an hour, and you're not changing, you're just staying at 60 miles an hour, then the force of the engine pushing forward is exactly balanced out by the force of friction in the air, and also internal friction, the parts of the car holding it back, okay? And the car is not changing speed. You're still moving, but you're not accelerating, okay? So the forces are balanced. All right, okay. Let's get into a little bit of technical knowledge. Forces are measured in the units on forces. Are something you're all familiar with. It's a typical one is a pound. Forces are measured in pounds, all right? You're saying, well, that's what I see on my scale. Yeah, because gravity is a force, and what you're, when you step on your scale, what you're measuring is the force of gravity on you, okay? How many pounds is gravity pulling down on you with, all right? And that's what the scale is measuring, all right? There's also a ton. And I'm giving you this, and I want you to know these because these are common things that we do, like these are common measurements that we use in America, okay? So a ton is 2,000 pounds, and then there's an ounce for smaller things, all right? And an ounce is 1/16th of a pound. And by the way, pound is abbreviated as the symbols LBY, that comes from the Roman word or Latin word librum, like scales, balanced, and all that sort of thing. Okay, so now in the metric system, we're going to use, because we use a metric system in this class, the metric measurement, which is a Newton. And since you're an American and you think in terms of pounds like me, I will tell you that 1 Newton is about, and that's why I'm going to use the squiggly equal signs, it's about 1/4 of a pound. All right, to put it in terms that, you know, most Americans would understand. Because I don't know what a Newton is, but if you tell me, oh, 1/4 of a pound, oh, okay, I kind of got that. All right, so make sure you know that. All right, now, the next thing the book talks about is this thing called a fundamental force. Okay, force. And what does that mean? Well, there are three forces in the universe that are very mysterious to us. We know about them, but we don't know where they come from, and they are the cause of, ultimately the cause of all motion in the universe. What do I mean by that? Well, if I throw a ball up in the air, how did the ball start moving? Well, let's trace it back. Well, it started moving because my hand gave it some motion. It forced the ball. The ball didn't want to start moving on its own. All right, well, where did my hand get the force to do that? Well, it came from, you know, the muscles and the structure of my body. All right, where did my body get the force to do that? Well, I got it from the food that I ate. The energy to create that force came from the food that I ate. Where did that come from? Well, it came from either an animal or a plant. And if it is an animal, it was an animal that probably ate a plant. So ultimately that energy and that force came from the plants that I ate. Where the plants get it from, got it from the sunlight ultimately. Where did the sunlight come from? From the sun. So ultimately we could trace the ball being tossed initially back to the sun. Where did the sun get the energy from? Something called the strong nuclear force. Where did that come from? All right, we don't know. We have no idea where the strong nuclear force comes from. We have no idea how the universe makes that strong nuclear force that's inside nuclear reactions. That's where it stops. It seemed to have been created with the Big Bang. And how and why, not really sure. Have no knowledge of that, really. Okay, so there are three fundamental forces in nature that ultimately cause everything in the universe to move. And they are in order of weakest to strongest, the force of gravity. And you're probably saying, what are you talking about? Gravity is a very strong force. If you walked off a building, you'd find out how strong gravity is. No, gravity is actually the weakest of these forces. The only time you feel gravity at all is when you are near something massive, like a planet. That's why you feel gravity right now, because you're actually standing on top of this massive, massive object, at least compared to you, called planet Earth. Stars, galaxies, or collections of billions of stars produce a lot of gravity. But you have to have that immense, immense amount of mass to make it. All right, a little bit of mass does not make a lot of gravity. You actually are creating your own gravitational field around you, but it's so weak that it's not even noticed. The next fundamental force, which is much stronger, is called the electroweak. Okay, which has several aspects of it. One of the most common that human beings come in contact with is electricity. Electricity, okay? And the second most common is magnetism. Magnetism and electricity are actually the same force, okay? And a lot of people don't know that. They're two aspects. You can't make electricity. You can't have electricity without magnetism. You can, in fact, electrical currents make a magnetic field. All right, the two forces, the two aspects are always there together. Okay, you can't have a magnet or a magnetic field without some form of electricity. So the two are together. Okay, and then there's something called the weak nuclear interaction, which is part of the same force, which we're not really going to talk about. Okay, that deals with certain forms of radiation. Suffice to say, the second fundamental force is the electroweak force. The third one, okay, is called the strong nuclear force. And that is the force that holds the nucleus of an atom together. It is much stronger than this force and much, much stronger than gravity. Okay, if you think about it inside an atom, what you wind up happening, now we studied nuclear reactions and we did fusion and fission, and inside the nucleus of an atom you have these little particles, charged particles called protons, okay? And so on and so forth, and they're all hanging around inside the nucleus of an atom. All right, well, what's going on is with the protons is because they are positively charged, the electroweak force wants to throw them apart, and they do, right? Under normal circumstances, if you took two positively charged objects and you tried to push them together, they would start to repel each other. Like charges repel, opposite charges attract. Like it's the same way as if you took two like north poles of a magnet and you tried to put them next to each other, they would start to push each other apart. Okay, but for some reason that we don't understand, nature says that if you get them really, really, really close to within 10 to the negative 15th meters, a billionth of a billionth of a billionth of a meter together, all right? If you were to get them that close, suddenly this new force is created called the strong nuclear force, and it overcomes the electric force and it jams them together and they fuse. And we talked about that when we talked about the sun, the process that lights up the sun, which is nuclear fusion. Okay, so the three fundamental forces are gravity, the electroweak, and the strong force. Okay, all right. I'm going a little. I know I'm going a little over time. It's going to be a little bit longer video, but I'm trying to shove in a lot in a small amount of time. Now, normally we would spend a week or so on this, but we're running out of time, and everyone's also getting tired anyway because the weather's getting nicer, and Gina is starting to let the people of Rhode Island out again. So. And I know, I'm with you on that. So let's just cover this quickly. One of the forces that is very important to us as humans and to everything in the universe is a force of friction. Okay, friction sometimes works for you, sometimes works against you. It's the reason why once you get your car going, if you take your foot off the accelerator, your car will eventually slow down and stop. So you have to burn more gas in order to overcome friction to get where you're going. But sometimes you want it. If you think, like, how does your car stop? Well, what happens is they have these two pieces of metal, all right, called brake pads, and they jam together very, very tightly. And what happens is you get an immense amount of friction when that happens, and that's what stops your car. Okay? Why is there friction? Well, because at the microscopic level, no surface, write this down, no surface is completely smooth. Okay, if you think, like, for example, like, you know, if you imagine yourself standing on something smooth like the top of your desk or something, which obviously isn't sandpaper, all right, so it's not a rough surface, all right, but if you were to shrink and to the size of a grain of sand and then stand on like your desk, you would see that the surface of the desk is certainly not smooth at that level. It's got all these tiny little bumps in it and so on and so forth. And all surfaces are like this. In fact, there is no completely smooth surface known to human beings. So when you take two surfaces and you put them together, these little hills and valleys kind of snag on each other. And each little snag is a microscopic force, but when you multiply it by millions or billions, you get the force of friction. And that's what that's what causes friction. Now, there are three types of friction, and the first one is sliding. And sliding friction is what you get when you have just two surfaces running over each other. Okay, we call that sliding friction. And sliding friction depends on how tightly that the surfaces are put together. So it depends on the contact. And by that I mean how tightly they're pressed together. The more you press them together, the more friction you get between the two surfaces. Okay, it depends on the surface area. Okay, of the two surfaces, the more surface area that there is between or in contact, because remember friction is a contact force, the more friction you're going to get. Okay, and it also depends on the roughness of the surface. Okay, so two pieces of sandpaper stuck, you know, like on top of each other are going to generate more friction than, like, for example, just two normal pieces of paper without the sand on it. Why? Because the sand makes it rougher, and you get more of these snagging processes. All right, so that's the first type of friction. Much less than sliding friction is the second type, which is rolling. And rolling friction is the type of friction you get between a curved surface and a flat surface, or two curved surfaces. So that's, for example, the reason why a wheel works. So if you have a wheel, okay, and you can see there's your axle right there, okay, and there's your flat surface, which is the road, you get much less friction, okay, between the wheel and the road. And here's what I mean by this. If you put your car in neutral, and you can push a car. It's hard because the car is so massive, but you can do it. And that's rolling friction, because the tires will roll, all right? So you put your car in neutral, all right, and then you can push your car, the tires will roll, and you can actually do it. Try pushing your car, pardon me, when your car is in park, so that the tires don't roll. Now try doing it. And I would doubt that you can. Why? Because when the car is in neutral, you get rolling friction between the tires and the road, which is much less. When the car is in park, you get sliding friction between the tires and the road, which is much, much more, okay? So rolling friction is a lot less, and that's the reason why a wheel works, okay? All right, and the third type of friction is fluid friction. Okay, and that's the type of friction you get between a fluid and a surface, or between two fluids, all right? You get friction. You actually do get friction between two fluids, and we see this in the weather all the time. It's the reason why you get lightning strikes. When a hot air mass and a cold air mass bump into each other, there's actually, and one goes over the other, there's actually a lot of friction in that boundary right there, and you can get a lot of static electricity, and you get lightning strikes. Fluid friction depends on several things. It depends on the surface area also, which is the reason why a parachute works. Okay, when you jump out of a plane, your body profile doesn't have a lot of area to it, and so you won't get a ton of fluid friction enough to slow you down to a safe speed. All right, when you deploy a parachute, what happens is you're increasing your surface area immensely, something like 10 times, okay? And the fluid friction between the air and the parachute and human being combination is a heck of a lot more, to the point where it slows you down to a speed that is safe to hit the ground at without hurting yourself or dying, okay? It depends on something called fluid viscosity, which is how thick a fluid is. So air is kind of easy to walk through, all right, and run through. Try running through water. Water is more viscous than air, and that's a workout. Why? Because it doesn't get out of your way as easily as the air does. And then the third thing is speed. It depends on how fast you're moving through the fluid. If you move through a fluid slowly, you don't get a lot of fluid friction, but the faster you move through the fluid, the more the fluid pushes back on you, the more fluid friction you get. Okay, I've talked for 22 minutes already. It's a longer video than usual, but again, I'm kind of going faster, so bear with me on that. Okay, so read through section 12.1, do the worksheet on it, see me during my office hours, and remember, especially now, since the weather's getting better, to enjoy your apocalypse. Call us out.